Okay, in this lecture series, we're going to be covering inclined planes. So for example 1, a block with mass m slides down an incline at a constant velocity. The incline makes an angle theta with the horizontal. Find the coefficient of friction in terms of the mass, the acceleration due to gravity, and the angle theta, which is the angle of the incline. Okay, so the first thing we're going to do is we're going to go ahead and draw our free body diagram and our motion diagram. For this problem, it is sliding down an incline at a constant velocity. So what we're going to do is we're going to go ahead and let me just sketch this out for a second. Here we have an incline, which makes an angle theta. Okay, we have a block sitting on that incline, and it's sliding down at a constant velocity. Okay, so the first thing we're going to do is we're going to go ahead and draw our motion diagram. And because we're moving at a constant velocity, that means that all of our velocity vectors have to be the same length. And that means our acceleration has to be 0. Okay, so now we're going to go ahead and draw our free body diagram. This gets a little bit complicated in drawing it because we're working with angles, but I'm going to show you some tricks. And we're going to be using that parallelogram method again, like we used in the hanging sign. Okay, so what's physically touching the block? The ramp, that's right. Is there friction? Yes, there is, because we're asked to solve for the coefficient of friction. So the ramp is supporting it, and there's friction, so that's 2. What's acting at a distance? The Earth. Are we in equilibrium? Yes, we are. So we have 3 forces, and we're in equilibrium. So the first thing we're going to do is we're going to draw the weight. So I'm going to go ahead and draw the weight going straight down. Okay. And then what I'm going to do is I'm going to lightly pencil in the inclined surface. Okay, so there's my inclined surface. And now what I'm going to do is I'm going to take this weight and I'm going to make it go up as a dashed line. Because it's not really there. I do know that my other 2 forces have to add up to give me this upward piece. Okay, now here's the thing. I know that I need to make a parallelogram with this, so I'm going to take the surface and I'm going to line it up like this. Okay, so that gives me 1, but I need another 1. So how am I going to draw that? Well, if I draw a line that's perpendicular to the surface, that will give me my other direction. So that's my perpendicular to the surface. And now what I'm going to do is I'm going to drag this over and put 1 right there as well. Okay, so now I have drawn my parallelogram, my box, around this upward vector. So I know that my normal force is going to be directed perpendicular to the surface. And I know that my frictional force is going to be directed up the surface, or up the ramp, to keep it from sliding down. So this is F on block by ramp. This is force on block by earth. And this is force on block by ramp. Okay? You may need to do this a couple of times until you figure it out. Now, here's the tricky part. Now that we've drawn our free body diagram, we have to do some of the forces. We only have 1 force that's going vertical, and that's the weight. And that means that we're going to have to break the frictional force and normal force up into components. But that becomes complicated the more and more forces we add into the problem. And so here's what I propose. Instead of making our reference frame horizontal and vertical like we have been in the past, what I suggest we do is that we take our reference frame like this and we rotate it like this. So in other words, our normal force and our frictional force will actually be on our x and y axes, and only the weight will be directed downward. So I'm going to make this my x-axis, and I'm going to make this my y-axis. And you can go ahead and do that anytime. If it's going to make the problem easier to solve, you just rotate your reference frame. Okay, so that's exactly what we've done here. We've rotated our reference frame. Okay, so now what we're going to do is we're going to sum the forces in the x and y direction. I'm going to go ahead and fold my paper in half. So I have x on one side and y on the other. Okay, so here we have the sum of the forces in x equals max. Here we have sum of the forces in y is equal to may. Now, since we've rotated our reference frame, that means that we have to break the weight into components. Well, that gets a little bit tricky. So I'm going to do that on a separate sheet of paper to show you the geometry behind that. So let's go ahead and draw our incline. Here's our angle. Okay. Let's go ahead and put our block right there, and our weight is going to go straight down. And we want to break that weight into components. Well, this is the x-axis, but we need the y-axis. The y-axis is drawn perpendicular. Just want to make sure I have this perpendicular. There we go. Okay, and this is my y-axis. Okay, I know that if I were to draw this straight down, that this would form a 90-degree angle. Okay, this is theta, this is 90. That means that this angle right here has to be 90 minus theta. Okay, this is also a 90-degree angle. Okay, this angle right here is also a 90-degree angle. That means that this angle right here, which is what we're looking for, plus the 90 minus theta must equal 90. Okay, so 90 minus theta plus my unknown angle has to equal 90 degrees. Okay, if I add theta to both sides, I end up with 90 plus my question mark is equal to 90 plus theta. Well, the 90s cancel out. I can subtract 90 from both sides. So my unknown angle is actually going to be equal to the angle of the incline. Okay, this is the angle that we want to use because this component is parallel to the x-axis and this component is parallel to the y-axis. So if I were to draw my x and y components, this would be my y component and this would be my x component. Okay, so this piece here and this piece here are my x and y components of my weight. So if I label this, I'm just going to use a shorthand just for the diagram. This is W, this is WY, this is WX. Opposite over hypotenuse is going to be the x component. Adjacent over hypotenuse is going to be the y component. You may need to look over this a couple of times and replay this over and over again until you finally figure it out. It does take some time for some students to get the finessing of how to break the weight into components. Okay, so let's go back. Now that we know how to break our weight into components, we're going to sum up the forces. So here we have, in the x direction, we have the frictional force, force on block by ramp, plus the x component of the weight, force on block by Earth subscript x, and that's equal to ma sub x. Am I accelerating in the x direction? No, I'm not. So this goes to 0, Newton's first law. Now I substitute in magnitude and direction. Remember, the subscript x turns into a sine or a cosine. And remember from our previous example of breaking the weight into components that the x component is the sine of theta. So we have minus mu sub s, because I'm not moving, I'm at rest, times the normal force magnitude, force on block by ramp, I hat, plus force on block by earth, sine theta, I hat, equals 0 newtons I hat. Now, this is where it gets tricky, because it's difficult for students to understand why they have to have the weight in the x direction. It's only because we've rotated our reference frame that that's the case. Okay, so for other problems at which you have angles, do not assume that you're going to be breaking your weight into components. You won't. Okay, so we're going to cross out our unit vectors. Okay, and now we're going to go ahead and solve for an unknown. What are we looking for? We are looking for the coefficient of friction. Well, here's the problem though. Here's the coefficient of friction, but we don't know the magnitude of the normal force. So I need to go to the y direction before I go on with this. Okay, so adding up the forces in the y direction. I have force on block by ramp plus force on block by earth subscript y, and that's equal to ma sub y. Again, this is probably going to be a little tricky for you understanding this. Wait a minute, isn't the weight always in the y direction? No, remember, we've rotated our reference frame. And so now our weight is actually at an angle, and this angle is the angle theta. So we're really trying to solve for this piece right here, and we're solving for this piece right here. Okay, we're solving for those two components. Don't draw them on your paper, because you don't want to draw the components on your free body diagram. They shouldn't be there. Okay, are we accelerating in the y direction? No, we're not. We're not moving in the y direction. Okay, we're not accelerating up and down off the ramp. Okay, so what we're going to do is substitute in magnitude and direction. I have force on block by ramp, j hat, minus mg j hat equals 0 newtons j hat. My j hats are going to cancel out. Oops, I'm sorry, cosine theta. Thank you, those of you that yelled out, woo, woo, woo. I appreciate that. I got your psychic message. Okay, so it's mg cosine theta. So I have force on block by ramp is equal to mg cosine theta. Okay, so notice here the normal force is no longer equal to the weight. Okay, remember, this is not always the case, so you have to be careful. You have to look at the scenario. Okay, we can now substitute this in right here. So now I have minus mu sub s mg cosine theta plus force on block by earth sine theta is equal to 0. Now this can be replaced with mg, and I probably should have done that up here. Okay, I should have done that up there. So let me rewrite this. Mu sub s mg cosine theta plus mg sine theta is equal to 0. Okay, I'm going to take this to the other side, and I end up with mg sine theta is equal to mu sub s, cosine theta. I'm going to divide both sides by mg cosine theta. The mg's cancel out, and that means that mu sub s is equal to tangent theta. Now, do not memorize this. This is a block stationary on a ramp. Actually, it isn't. It's moving at a constant velocity. Sorry. This is a block that is sliding down a ramp at a constant velocity. What if I were accelerating down the ramp? This would change, right? So the only way you can find the coefficient of friction by using the angle theta is if you are at rest or you are moving at a constant velocity down the ramp. Okay, that is the only time mu sub s or mu sub k, sorry, this should be k's then if we're kinetic. Yep, we're moving. Sorry about that, guys. Change all these to k's. Now you're getting a real lecture because this is exactly what I do. I make a mistake at the beginning and I carry it all the way through, and then at the end I realize I've made the mistake. Are you allowed to do that? Of course you are, as long as you turn in the correct answer at the end. That's the important thing. And recognizing that there's a mistake. Okay, so mu sub k is equal to tan theta.